Okay. Maybe I can start introducing our speaker today. So thank you everybody for coming to our seminar. So Jorge Lillo-Box is a researcher at the Center for Astrobiology in Spain. Previously, he worked at the European Southern Observatory in Chile and worked on instruments such as Extruder and Espresso. He then joined the Center for Astrobiology as a postdoc in 2019 and recently obtained a permanent position as a research scientist there. His main research is focused on obtaining and analyzing high-precision radial velocity data and light curves to detect and characterize planetary systems. And currently, his team at the Remote Worlds Lab is focusing on two projects. One is the TROY project for the detection of the first orbital planets, and the second is the Kobe experiment for the detection of rocky planets in the habitable zone of late K-type stars, which he will talk about in the seminar. So, Jorge, thank you so much for coming, and the floor is yours.
Yeah, thank you. I'm gonna share the screen. Thanks for the introduction. Still, I hope you can see.
Yeah, all good.
Presentation full screen. Okay, excellent. So, good morning, everybody in the US. Good afternoon here in Spain, where I am now. It's a pleasure for me to give this seminar. So thanks also Ravi for inviting me and Stel for hosting me. My name is Jorge Lillo-Box, as Stel mentioned. I am a research scientist at the Center for Astrobiology in Madrid. And today I'm going to talk about the Kobe experiment, which is a project that we are leading from my host institution, but it's also a collaboration among different European institutions like the Laboratoire of Marseille and the Institute of Astrophysics of Portugal. So before entering into the talk, I would like to take this opportunity to give you a very brief summary of the Astrobiology Center in Madrid so that you can locate where we are and the kind of science that it's done in our center. So you are here, more or less, I guess, and the Center for Astrobiology is located in Spain. Inside Spain, it's located in the Madrid area. And indeed, the Center for Astrobiology is split into two main facilities. One is located in Torrejón de Ardoz at the northeast of Madrid city, and the other one is in Villafranca del Castillo at the west side of Madrid city. Here are the two buildings, this one in Torrejón, this one in Villafranca. The one in Villafranca is located inside the facilities of the European Space Agency. So we are not part of it, but we are inside their facilities. So we have a lot of connection with researchers at ESA. So the Center for Astrobiology, we are around 200 researchers, and we are split into 4 main departments, with very cool names, as every astrobiology center, I guess. But that I am very, very astonished when I saw the names of the departments for the first time. We have a Department of Molecular Evolution, which where they study the processes that have that facilitated the emergence of such a degree of biological diversity on a planet that was initially inert. Then we have the Department of Planetology and Habitability, where the people there study the extreme environments to understand the interaction between geology, biology, and the physical conditions that allow a given environment to be habitable, mainly in the solar system. Then we have the department with the most boring name, the Department of Astrophysics, which is where I belong to, and we study the processes that were necessary for the emergence and evolution of life in the universe. And then we have the Department of Advanced Instrumentation, where they develop new instruments and new technologies for planetary astrophysics, and so instruments capable of detecting signs of biological activity. So as I mentioned, I belong to the Department of Astrophysics, and I am currently leading a group of PhD students and a postdoc that is coming soon, which is named the Remote Worlds Lab, and which is located in the building at ESA facilities. Okay, the main focus of the Remote Worlds Lab is the detection and characterization of extrasolar planets, with the focus in habitability and in regions of the parameter space that are sparsely populated. So you can visit our website, it's this one, to learn more about the different projects which we are leading, which are shown here. But in this talk, I'm gonna focus only on one of our main projects, which is the COBE experiment. So I would like to start this talk by revisiting a little bit the concept of habitability, so that we are all aware of the concept and how it is interpreted in the exoplanetary field, because this concept is important for this COBE experiment. We know that life in our planet emerged very early, since our world became habitable. So the abiogenesis does not seem to be a very complicated process in worlds like our own, but however, we know that worlds beyond our solar system are very much diverse than our own planet. So how can we know which among those planets, which are very different from ours, are more favorable to develop and sustain life, and how that depends on the different properties that they have? So to that end, we define the concept of habitability as the degree in which a given environment can maintain life. It's interesting that here when we talk about environments, we mean either local environments, if we refer maybe to Earth or solar system bodies, or general planetary scale conditions. For life to develop, at least as we know it on Earth, this is so for this step from chemistry to biology to happen, we need three basic ingredients, which are an energy source, an appropriate chemical elements, which in our case are those known as chumps: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And then we need a solvent that allows the transport and mixing of these elements. In our case, the solvent is water, as you all know. And for these three ingredients to be found on a planet, there are several conditions at a macroscopic level. The main star around which the planet orbits, first, the architecture of the planetary system, including the different interactions between the different planets, but also the intrinsic properties of the planet. In this talk, I'm going to discuss very briefly the energy source and the solvent and how they depend on the stellar type, because this is important to understand the reasoning behind why we propose the COBE experiment. So first of all, the spectral type of the star will determine the amount of energy that it emits. And this, combined to the orbital period of the planet, will in turn determine actually the amount of energy received by the planet. And this is critical to determine the habitable zone, as you all know. But also, the spectral type will determine the time spent by the star in the main sequence. And this is critical for the development and sustainability of life, as this period, the main sequence, is the quietest in the life of a star. Obviously, not only the amount of energy emitted by the star matters, but also how this energy is distributed in the electromagnetic spectrum. So the hottest stars have their maximum emission at bluer wavelengths, while the cooler stars do so in the red part. And this is crucial because that drives the type of life that can form on a planet. In our Earth, for instance, the sun emits at its maximum in the yellow color and at about 550 to 600 nanometers. And that causes plant photosynthesis to produce this greenish color that plants have. But in addition, low-mass stars are convective, are fully convective, which generate important magnetic fields with large flares and high UV radiation that threatens life on planets. During their formation, in what we call the pre-main sequence phase, stars also emit significant amount of UV radiation. In late low-mass stars, this phase can last up to 2.5 gigayears. It's a lot, 2 orders of magnitude longer than a star like our sun. So a long duration of this phase could cause the atmosphere of our rocky planets to erode at very early stages and end up being lost. Another effect is that after reaching the main sequence, the luminosity of low-mass stars stabilizes for periods of time longer than the age of the universe, indeed, while in stars like the sun, there is a gradual increase in luminosity. For example, the current sun is 30% brighter than when the planets in the solar system formed. And also it's important to note that just an increase of 10% more than the current luminosity of the sun would imply the evaporation of the Earth or Earth's ocean. The last ingredient is solvent, which in our case is water. Water is a molecule, is one of nature's best design. Its polarity makes it capable of keeping a multitude of compounds with many biomolecules in solution, which allows their transport and encounter with other compounds, facilitating multiple tests of chemistry to become biology. For example, it has a high range of temperatures at which it remains liquid with a relatively high boiling temperature. Its surface tension and capillarity make it an ideal compound in the formation of membranes, etc. It has a lot of properties which are very cool for life as we know it. Even though we could imagine that life could develop based on other chemical compounds, however, water is the most abundant chemical element in the universe. And to be honest, I think it has unbeatable properties for life as we know it. Other solvents are possible, such as methane or ammonia, but they present many problems that would be very difficult to solve for life as we know it on Earth. So the habitability of a planet, but more importantly, the options for a planet to originate life seem to depend on the existence of liquid water on its surface. When we talk about the term habitability, we are also referring to our ability to detect life in that environment remotely. So for this reason, in exoplanetary systems where visiting these worlds is an absolute chimera, the habitable zone has to be defined as a liquid water zone. And I like that definition best, actually. This habitable zone is defined according to Castin and collaborators as the region around a star where a rocky planet could maintain liquid water on a geologically active surface. It's a very simplistic definition, and we all know that already that being within the habitable zone doesn't mean anything actually in terms of inhabitability of that planet, but it's a good focus in the remote search for life. So its location strongly depends on the stellar spectral type, and this has key implications in our search for habitable planets. But let's say that we can select the ideal properties of a habitable planet and its star so that we can detect it with our present telescopes. What is the wish list for the properties of such planet? What would be the ideal case? Let's make a wish list of properties. First, we can make a wish list related to the true habitability of the planet, beyond being within the habitable zone. This is conditions other than being within the habitable zone that would be ideal for the planet to sustain life. Of course, the first thing we want is that the star can form rocky planets within the habitable zone, obviously. This is a priori not a problem for any of the spectral types that we are considering in this talk, which are J, K, and M stars. Second, we want the habitable zone to be relatively far from the star for different reasons. First, we do not want the planet to receive a huge amount of extreme UVs and X-rays that can erode its atmospheres or directly damage life on the surface of the planet. Second, we also do not want stellar flares to directly impact on the planet. And third, we may want to avoid tidal locking because although some works have shown that life is possible on tidally locked planets, it clearly difficults the possibility of life on a planet. Now, all these conditions are met in G-dwarfs because their habitable zones are relatively far away. They are more or less met within the K-dwarf regime, but they are absolutely not met within M-dwarfs. M-dwarfs suffer from their habitable zones being very, very close to the star, and these stars being very, very active. So also, it's important that they show small changes in luminosity, so that they don't flare, or at least they flare not much, and then that they have relatively short pre-main sequence lifetimes, as I mentioned before. And this is met by G-dwarfs, more or less by K-dwarfs, but not by M-dwarfs. The second wish list that we can make is the detectability. It's about the detectability. We want a habitable zone sufficiently close to the star so that, first of all, the radial velocity amplitude is large enough to be detected by our current instrumental limitations, but also, if possible, so that the transit probability is relatively high. In the case of G-dwarfs, the habitable zone is far away, beyond more than 100 days, 150 actually days in the best cases. And on the other side, in M-dwarfs, the habitable zone is very close as a few days in the later types. For K-dwarfs, this regime is between 50 and 200 days. So the radial velocity signal of a 10 Earth masses planet is easily detectable in the K and M-dwarf domains, while it's very challenging in the G-dwarf domain. Also, the transit probability within the habitable zone increases with late types up to around 3,500 degrees. So late Ks and early Ms, again, are ideal for this. But stellar activity is, however, larger on M-dwarfs, increasing the radial velocity noise even above the planetary signal amplitude. Also, magnetic cycles are longer in K-dwarfs, which reduces the confusion within the habitable zone periods. And last but not least, the determination of stellar parameters in M-dwarfs is very complicated, especially those related to chemical abundances. And this challenges the inference of stellar properties and hence the planetary counterparts. So overall, I think we can convene that K-dwarfs are the Goldilocks environments for detecting planets that may be truly habitable within the habitable zone. So let's see what we have obtained for now within the exoplanet exploration, within the more than 30 years of exoplanet exploration. And this section, I call it the K-dwarf habitable zone planets, and I am spoiling here myself because, as you will see, there's no. It's actually a desert. So I start this section now with this famous diagram where we show the stellar incidence flux in the x-axis. In units of the flux received by Earth from the sun, and in the y-axis, the effective temperature of the star. I put here Venus, the Earth, and Mars. Here you have the G-dwarfs, the K-dwarfs in the middle of the diagram, and the M-dwarfs in the bottom part of the diagram. I am going to include the planets that have been detected along the past years. And I will use this legend here, where I will put open triangles for radial velocity detected planets. So we only have the minimum mass. open squares for when we have the few cases we have radial velocity plus other techniques that allow us to obtain absolute mass. When I say other, I mean other but transits. I will use field circle, red circles for radial velocity plus transit detection, so that we have absolute mass of the planet and radius. And I will use open blue circles for transit-only detected planets. This means that the planets are only validated and not confirmed, meaning that we don't have their masses. So if we move on from the 1990s a little bit, the first planets start to appear here, and we stop in 2009, and we see clearly that first planets were detected within this regime, which is it's a small part of the parameter space, I must admit, but it's the habitable zone. I didn't mention it, but I assume you know it. The green shaded lines, green shaded regions are the habitable zone, the optimistic habitable zone, and the conservative habitable zone in darker color. So as you can see, within the first 15 years of exoplanet exploration, more or less, all planets in this regime were detected by the radial velocity technique. And interestingly, all of them were detected around G-dwarfs. This is potentially because because we focused on this type of stars, because our star is a G-dwarf. And also because our instruments were made primarily for stars like our sun, so focusing on the optical regime. So we move on a little bit to 2015. Kepler was launched in 2009. So it started to detect planets, smaller planets, and planets in the habitable zone, and start filling. It started filling this regime, especially in the case of low mass stars, where new planets started to appear in 2015. And this is the picture today. The new instrumentation has allowed us to really go down in masses, because here the symbols are proportional to the sizes or masses, depending on what we have. So we are detecting smaller or lighter planets around smaller stars, like the M dwarfs. But because you're very smart, clever people there, I guess you're already seeing something in this diagram that is clear to the eyes of everyone, and it was when I thought about the Kobe experiment, and is this relatively empty region here, which I call the K-dwarf habitable zone desert. As you can see, there are very few planets within this regime, and basically all but one or two are only are planets detected by the transits method, and they are not even confirmed. They have no masses except for 1 or 2, 3 cases here. So there's a dearth of planets in the habitable zone of late type K-dwarfs. And we may wonder if this is an observational bias, if it's a consequence of planet formation for whatever reason, or if it's both or whatever other reason. And the first exercise that we can do is it's to plot here a kernel density histogram. Here in yellow, I'm showing the KDE of all planets in this plotted in this diagram within the habitable zone only, including those that are validated. And as you see, there is a peak around G-dwarfs, and then there's this desert around K-dwarfs, and then we have a new bump here around M-dwarfs. It's basically the same if we only take into account the confirmed planets, so those where we have mass measurement. So this is interesting. It's clear that there is a dearth of planets here from these histograms, but it's interesting to compare this with the expected occurrence rate of planets in this regime. And thanks to several works, we could obtain the occurrence rates for several spectral types and subspectral types. We came up with this black histogram here, where there are two things interesting: the bump within the late K-dwarfs, which is telling us that we should expect a large fraction of late K-dwarfs to have planets on one side, and then the other aspect is the large error bars of the histogram in this regime, which is telling us that very few late type K-dwarfs have been monitored, have been explored in the past during the exoplanet exploration phase in the past 30 years. So far, we can only work with the hypothesis that this desert is due to an observational bias, mainly because we have not even explored in depth this region. And this is how the Kobe experiment idea came up. And I'm going to talk about it for the rest of the talk. So the Kobe experiment was born thanks to a call for legacy proposals of the Calar Alto Observatory. The Calar Alto Observatory is one of the best observatories that we have, I would say, in the world, and certainly in Europe, because it has a lot of good nights per year. It has 3.5 meter telescopes and another 2.2 meter telescope, and state-of-the-art instrumentation like the Carmen's instrument. So the observatory launched a call for legacy proposals where the community had to propose projects, long-term projects requiring a lot of nights, basically, which in any other observatory you couldn't do this, actually, with such a good instrumentation. So it was really a good opportunity for projects like the Kobe experiment. So we prepared a proposal and we got the time. We got around 200 nights to be used within 2.5 years, so 5 semesters. So around 30, it was like 35 nights per semester, plus backup nights in case of bad weather. And we recently obtained an extension because it finished in June 2023. So we got another 135 nights, and we are extending the mission until the end of 2024, which is very good. So this proposal was accepted, and they gave us all these nights with the Carmen's instrument, which is, I will talk about it in the next slide, to monitor 50 late type K-dwarfs from spectral types K4 to M0 to populate the late K's habitable zone desert and test this scenario of observational bias, at least to be able to say there are no planets, or maybe there they are, and it was just that we didn't focus on these spectral types in the past. The results of this project will be very interesting for for missions like JWST, which is already flying, and future missions like Plato, where our institute, Center for Astrobiology, has a relevant participation. And also, it will be very interesting for future missions from the European Space Agency and others from NASA, like LIFE, that we are proposing to ESA. So the Kobe experiment is described in this paper here that came out at the end of last year, and you can visit the website here for additional information. So all these nights were granted in the 3.5 meter telescope of Calar Alto, which is located in the southeast part of Spain. The telescope is this one. And they were granted with a Carmen's instrument, which is visible and near infrared. It has 2 channels, stabilized a spectrograph that is able to reach meter per second precision. in the visible channel and around 5 meters per second in the near infrared channel. So a very good instrument, which has already detected several tens of planets around M-dwarfs from the Carmen Science team. And they were published very recently as well. It's a very interesting paper that I encourage you to read as well, from Ignacio Rivas. But so the COBE experiment is another project. As I was mentioning, we sent the proposal in 2020. It got accepted by mid 2020. We started the observations in 2021. The prime mission, so the 200 nights, lasted until June of this year, and then we started the first extension that will last until the end of next year. So what can we expect from the COBE experiment? What is the yield that we expect from the COBE experiment? We can do a small exercise. We did it before for the proposal using these occurrence rates from Kunimot and Matthews in 2020. We use these tables which show the occurrence rate per period and radius beam. I hope you understand, you already know, you're already familiar with this kind of diagrams, where each beam tells you the occurrence rate, so the percentage of stars that can host a planet within this period range and radius range. So for the first thing we have to do, so this is for K-type stars. And the first thing we have to do here is to cut planets that are not detectable by Carmenes, just simply because of instrumental precision. We are assuming here a precision of 1.8 meters per second to be conservative. And there are other assumptions that we are going to do in this exercise, which is that this diagram is mainly built with early K-dwarfs. We are assuming the same occurrence rate values across K-type subspectral types, which might not be fully correct, but it's a good approximation. We are also assuming that we can detect planets if the radial velocity semi-amplitude corresponds to 3 times the uncertainty that we have in our measurements, and we are not taking into account the activity in this exercise. So the first thing we can do is integrating this diagram on the detectable part. And if we do that, we get an occurrence rate of planets in K-dwarfs with periods below 400 days that are detectable by Carmenes, so this occurrence rate is around 1.7 planets per star. So since we are observing 50 stars, the expected yield of the COBE experiment is 84 planets, plus minus 13 in this exercise. We can also focus on small planets, here restricting the radius to 2.8 Earth radii. And in this case, we get an occurrence rate of around 11%. And so the expected yield of COBE small planets is around 6 plus minus 2. We can also do a habitable zone exercise here, restricting to periods which are within the habitable zone of late type K-dwarfs, which is this regime, basically. If we integrate all of it, we get 75% planets per star. So 0.75 planets per star, which means for COBE, for the sample of COBE of 50 COBE targets, we should detect around 37 plus minus 8 habitable zone planets of any radius. If we use on small planets, things get worse, of course, and we get a 5% occurrence rate in general. So COBE should detect between 0, hopefully not, and 2 small habitable zone planets. So that's the expected yield. In the paper that we published by the end of last year, all this is explained, and we also explained the sample selection that we did. using Gaia stellar parameters, using the effective temperature to make CATs between 3800 and 4600 Kelvin, targets that are visible from Colorado for at least 4 months per year. And all this gave us around 6,458 stars. From this, we use different metrics involving different parameters like the Gaia magnitude, an SED inspection, everything that we could fill in our metric. And we went from this more than 6,000 late Ks to we ranked the first, we ranked them based on this merit function, and we obtained a preliminary list of 200 late Ks. Then we inspected these 200 stars more in depth. We removed stars with close companions that were also fast rotators. We were left with 170 late Ks. And then we did a new metric based on the habitable zone coverage, the ability to cover the habitable zone, so that we have an homogeneous sky location of the stars, so that we have targets all the months in the year. We also inspected the X-ray emission, etc., and we came up with the final list of 50 late Ks. We also ranked the second backup list, let's say, with another 50 late Ks just in case during the first observations of the prime sample, we have to remove any of the targets. We inspected the test observations so that we could measure excess noise due to stellar activity, so that we were able also to reject eclipsing binaries and select the most quiet stars according to test observations, which by then we only had one sector for most of the targets. We also performed high spatial resolution imaging with Astralux to ensure that these targets are alone, and they are. All COBE targets are alone, at least to the sensitivity that we got, which is 0.2 arc seconds resolution and 5 magnitudes contrast. This is the visibility plots. These are the visibility plots of the COBE targets. This is just to show for every month, so that the shaded region shows the part of the sky that is visible on the 15th of each month. So that this is just to show that every month we have at least 10 targets, 10 COBE targets that are observable from Colorado. These are some of the properties of the final sample that we are observing now. All targets are closer than 50 parsecs. The mode of the effective temperature is around 4100 Kelvin. They are all brighter than 11 magnitudes in the Gaia band. And interestingly, they are slightly subsolar in metallicity because we didn't put any constraint on metallicity. So the final sample is slightly subsolar, which I don't really like a lot, but it's okay. It's what it is. The second result that so we published the description of the sample selection and everything in this paper in Lillo-Box et al. 2022, and we also published another paper, which is one of the first results of COBE in a paper by my PhD student Olga Balsalobre-Ruza at the beginning of this year. And she developed a code which I think it's very, very interesting for not only for the exoplanet community, but for anyone wanting to do observations that pursue a given period. So she developed COBE-SIM. COBE-SIM is an algorithm that improves the efficiency of the observations by using Bayesian inference. So what it does is I can talk about it in the questions if you want, but basically what it does is proposing the next observing date based on the information you have with the previous observations, given that you want to pursue a given period. So overall, as a summary of this COBISIM algorithm, what we can do, if you use this algorithm, you can save up to around 50% of the time. So you can detect the planets earlier. You don't need, and more importantly, you need around 30% less data points if you follow what COBISIM is suggesting you. Here are some preliminary results. Please don't tweet, of course. There are no names here, but I prefer if you cannot share this information, because they are preliminary results, and we are still in the process of preparing the papers and confirming the signals, etc. But I can tell you that we have detected several signals, and several of them are within the expected location. And this is one case where we see a very clear signal within the habitable zone of this K7 star. Interestingly, it has an eccentric orbit, but it falls perfectly within the late type K-dwarf desert. We have also detected we are also detecting long period planets, like in this case. This would be a cold Jupiter with an estimated period more than 800 days. And interestingly, it also fits very well with another planet inner companion, which is interestingly also within the habitable zone of this system. In this case, we have very few measurements, but we are starting to increase the cadence of the observations in this system now. We are not only detecting this type of planets, but we are also detecting short period planets. In this case, I am showing the case of a multiplanetary system with 2 planets which are potentially in 5-2 resonance, and we are detecting many different architectures in this 50 planet sample. So I would say that we are more or less in line with the expected yield that of the exercise that I explained before. So to conclude, looking for habitable exoplanets means following the water, of course, and follow the water when we talk about exoplanets means looking for habitable zone worlds. Unfortunately, the habitable zone of late K-dwarfs, despite being the Goldilocks environment from the detectability and habitability aspects, is empty. So the COBE experiment has taken the lead to start filling this very, very interesting regime from an astrobiological point of view. We are using the Carmenes instrument. We are following up 50 late type K-dwarfs within 3 to 4 years, more than 4 years actually. And the planets that COBE will detect and is detecting will be prime targets for atmospheric characterization with missions like LIFE and potentially others also from NASA. And that's it. Thank you for your attention. I'll take any questions you may have.
Thank you so much. Thank you so much. That was a great talk, very interesting. So while people are gathering their thoughts and questions, actually Ravi posted a question and a mark of being impressed when you showed the 0.75 value for the number of planets in one of your slides, and he's asking if you have any reference for this estimate. Ravi, by the way, feel free to ask your question. Yeah.
That's good. Thank you.
Can you repeat the question? Sorry, Estelle, I didn't.
Sorry. So at some point you showed in one of your slides that you expected 0.75 planet. The
Yes.
average occurrence rate within the habitable zone. Do you have any reference for this estimate?
So okay, so all this exercise is done using the Kunimoto and Matthews estimates from 2020, which is based on Kepler observations. So I'm just integrating this diagram over these bins here that are marked in blue.
Sorry, what was the reference you said, Jorge? The Kepler?
I think it's written here. It's Kunimoto and Matthews, 2020.
Oh, Michel's paper. Oh, I was on the paper. Okay, thank you.
Yes, Michel's paper.
Okay, I should have known this. Thank you.
Great. Any other questions? Oh, yes. Vladimir, please feel free to ask a question.
Yes, thank you for a very interesting talk. So my question about the sample size. What's the sample size for this K occurrence rates for super Earth and the Earth? And so for rocky planets, how many?
How many do we expect?
Well, how many do we have now? Do we have any? Or yeah, so what's the data show?
Okay, regardless of the spectral type of the star, you mean?
Mm-hmm.
So this?
Yeah, right.
I don't have
around K-dwarfs.
Around K-dwarfs, there are very few. They are all detected by transits. We don't have any. I would say only this case here, which I don't know what it is exactly, but these two are either giants or Neptunes.
Okay. Mm-hmm. Thank you.
Gaseous. Yes.
I have a question. So you said that you were awaiting follow-ups from LUVOIR and HABITS and potentially the LIFE mission. Is there any possibility to have like atmospheric follow-ups that are earlier than this? And do you think that we could already get an intuition for whether like the planets that are hosted by late K-dwarfs might have a higher chance of having an atmosphere than M-dwarfs? Like, do you think this is within the next few years, or do you think that it will have to wait for like the next generation telescope?
Yeah, that's a very good question, actually. Thanks. Yeah, the point is that, so there are no planets here. The only ones that we have are only detected by the transit method, which is good. And we should start thinking about getting masses of them. But this is very costly, of course, and we can start inspecting their atmospheres already because they transit. But since atmospheric transmission spectroscopy observations are very expensive, you really need to convince the panel that the planets are really there. So I would say that a validated planet will not pass that. So you really need masses, actually. So we are starting also a program to try to measure masses on those cases. And COBE planets are not expected to transit because we didn't make any selection based on that. So we might need to wait until observatories like LIFE fly, if they fly at all, in the 2040s. Because then with direct imaging, we will be able to point to these planets and get the atmospheres. And this will be very, very important. So that, there's a preliminary work, which is necessary, which is the one that we are doing, which is detect planets that we can confirm in this regime. And regarding the prospects for the atmospheres of K-dwarfs being, I don't know, I don't know if you said better or what was like the word that you used?
Like the atmospheres of the planets hosted by K-dwarfs. Like right now, like there's a bit of a crisis because like we don't know if the planets hosted by M-dwarfs have or like if most of them have atmospheres. So like, but this is like another question like that is more related to the activity of like K-dwarf stars.
Okay.
Ravi, you had a question. Do you want to ask it or?
I was just going to plug in the SEEK conference next April. it's on non-transiting planets, and actually I have to leave for that meeting in about a few minutes. Jorge, I'm going to post that link for the website here in the chat, and we certainly would love to have your group's presence over there. It's all about non-transiting ones, and this is very relevant.
Excellent. Thanks. We will be there.
Yeah.
Okay, well then I will ask Ravi's question that he posted in the chat, which is what was the minimum mass of the planet that you discovered around K7 star?
Sorry. What's the mass? You mean?
What is the minimum mass of the planet that you discovered around the K7 star?
So the case that I showed at the end of the talk, it's this one. It's in the sub-Neptune regime, so it's below 16 Earth masses. Yes.
Okay. Vladimir, do you I see you have your hand raised. Is that an artifact from the previous question, or do you have another question? Okay. Any other question from anybody in the audience?
I have a lot, but I want to wait for at least the other people and for young people to ask even more, please.
I mean, go for it, Ravi, please.
No, I'll write to Jorge later. So I think we should give this to others.
Okay, does anybody have another question then? Okay, so I guess I'll ask my detection question, which is or my stellar activity question, which is what is the consensus right now on like whether K-dwarfs are less active than M-dwarfs, to the extent that like exoplanet atmospheres would be more common around these types of stars, or like for terrestrial planets at least?
So that's a very good question. Our premise was that late K-dwarfs were not very active. And then we are finding that that might not be totally true. So that's one of the conclusions of our survey as well. We're finding we are sensitive to stellar activity in these K-dwarfs. In most of them, we see clear activity regarding rotation, but also magnetic cycles. So even though the imprints on radial velocity are lower than in the case of M-dwarfs, where you see huge offsets and variations due to this activity, you still need to take them into account in your analysis. It's not that they are below your sensitivity limits and you can just forget about them. You still need to work. It's less. It's affecting less than in M-dwarfs, but it's still an issue. Yes.
Okay. Yeah, that's great. I mean, if we can motivate more people using this type of like star in their modeling simulations, that would be nice. I know Data Army, like I thought it had done a paper like this, but more would be better. That's cool. Okay. Any last question from somebody else? And if anybody has more questions, feel free to email me, and I can like share them with Jorge a little later.
Yeah. Of course, yes. And also within our group, we are very open to collaborations. So if you think you have an idea that we can work together in this effort, I really love collaborating with people. So if you have ideas, if you have telescope access and everything, you are very welcome to write me, to email me.
Awesome. Okay, so if there are no other questions, I guess we can end here. Jorge, thank you so much again for accepting our invitation, and thank you for giving it a talk. I really look forward to getting the results of this experiment and like reading the papers. So thank you so much, and have a good evening, I guess, in Spain. Yeah, thank you everybody for attending, and have a good week until the next seminar.
Thank you for hosting.